Okay, so good afternoon, everybody, or good morning, Seyda, as you are in California. Thanks again for making this talk so early in the morning there. So today we have the pleasure to have Seyda Ipek with us. She's going to speak about a model for neutrino masses and the LHC. And if you want to make a question or a comment, just raise your hand and unmute yourself and just make the question. If it is okay for you, Seyda?
Yeah, sure.
Okay, so please go on.
Yeah, thank you very much. I wish I was in Madrid, and I wish there wasn't a pandemic going on around the world, but this is, I guess, the second best thing. Yeah, so I'm going to talk about neutrinos today, and sorry, don't know why my arrow buttons wasn't working. So, as we all know, neutrinos are amazing particles. They have masses and they also go under what is called oscillations. These are neutrino oscillations because neutrino mass eigenstates do not align with the flavor eigenstates. And this causes an oscillation between the three mass eigenstates, and these mass eigenstates are a linear combination of the flavor eigenstates electron, muon, and tau neutrino. So this is one thing we know about the neutrinos. And this mixing can be described well with a 3x3 matrix called the PMNS matrix. This is the neutrino mixing matrix. And so far, we measured the three mixing angles between the neutrino masses. We also measured mass differences between the mass eigenstates. However, we don't know the masses of individual neutrino mass eigenstates yet. We also don't know the mass hierarchy because we haven't measured the sign of the mass difference between 3 and 1 mass eigenstate yet. So that we don't know the mass hierarchy, meaning which if the neutrino with the littlest amount of electron neutrino is the heaviest or the lightest. We don't know this yet. We also don't know if there's any CP violation in the neutrino sector, although maybe recently this might have been measured. So the CP violation is described by this phase delta in the PMNS matrix. So these are stuff that we do know and we don't know about neutrinos. And even when we know that neutrinos have masses, we actually don't know where that mass comes from. Because since right-hand neutrinos haven't been observed in the standard model, it was thought that neutrinos are massless for a long while. But then when we observed neutrino oscillations, we knew that they have masses in nature. So this was a dilemma or a problem within the standard model, basically, where the neutrino masses come from. So this, the original neutrino masses is not known, but there are, of course, many new physics models. There are physics beyond the standard model models to explain the origin of neutrino masses. The first explanation, and I'm going to talk about kind of three general cases of models. The first one is basically just adding like a standard model like masses. So these are basically say the neutrinos are exactly like the other standard model fermions, and they get a Dirac mass. There's a right-hand neutrino, which is a standard model singlet, and through the Yukawa term, when the Higgs gets a vacuum expectation value, neutrinos get their masses, exactly like an electron or any other fermion in the standard model. And in this case, of course, the Yukawa coupling that couples a neutrino right and left-hand neutrino needs to be about 10 to the minus 12 to explain the smallness of neutrino masses. So even though we don't know the exact scale of the neutrino masses, we know that it should be around EV or so. So this is okay. This is a very small number, but fermion masses are technically natural. So this if this was 0, there's a symmetry that is restored. So maybe it's okay for this number to be small, but it's still much smaller than any other Yukawa coupling we have in the standard model. For comparison, the electron Yukawa is about 10 to the minus 6. So as particle theorists, most of us don't like very small numbers, basically. So this is why there might be a problem with this explanation. The second way to give mass to neutrinos is by using Majorana masses instead of Dirac masses. This is the well-known, well-studied seesaw mechanism. In this case, the neutrinos are considered to be Majorana particles instead of Dirac. So in that case, you can write the Yukawa term and also a Majorana mass term for the neutrino. Here, MR is the Majorana mass term, and the neutrino masses, or the light neutrino masses, are proportional. Are inversely proportional to this neutrino, to the Majorana mass. So for example, an order 1 Yukawa coupling between the Higgs and the neutrinos, if the Majorana mass is about 10 to the 14 GeV, you get the right neutrino mass scale. So here you are basically saving yourself from having a very, very small number in the expense of a very heavy Majorana mass scale, or a seesaw scale. Of course, you can live with maybe a smaller Yukawa coupling, and then this would reduce the seesaw scale. So it's a play you can play, but still there's the light neutrino masses are related to a very heavy thing, and it's called the seesaw mechanism. And in this case, since the neutrinos are Majorana particles, that lepton number is violated. And this is an accidental symmetry of the standard model anyway, so it might be okay that lepton number is violated. Also, particle number in our universe is already violated because we have a matter-antimatter asymmetry. So even though there is a broken symmetry, there could be this could be actually a good thing. So this is the seesaw mechanism. The third third class of models is called the inverse seesaw mechanism. This is basically combining the two cases, the Dirac and the Majorana case. So in this scenario, neutrinos are actually pseudo-Dirac particles. And there's a mixture of lepton number violating and conserving terms in the neutrino mass Lagrangian. So to see this, you add two standard model singlets, fermions, to the standard model. So you n and n prime with opposite lepton numbers. So say n has lepton number +1, n prime has lepton number -1. And then you write down all the mass terms you can write down, basically. So the first line here has the Yukawa term between the lepton doublet and n, and a Dirac mass term. So these are lepton number conserving terms, these two terms, and then the next next three terms are lepton number violating. So this is the lepton doublet and n prime, and then there are the two Majorana terms for n and m prime. So this is a more complicated, a bit more complicated Lagrangian. Excuse me. And so if you go ahead and find the light neutrino masses, or the masses of the standard model neutrinos, this time they are actually proportional to the Majorana mass. So they are proportional to the Majorana mass times some Yukawa couplings over the Dirac mass. So in this case, and here mu is the Majorana mass. So with order 1 lepton number conserving terms, these are the Yukawa terms, and maybe a TeV scale right-handed neutrinos. And in order to get the correct neutrino masses, you require small lepton number violating parameters. For example, yn prime is a lepton number violating Yukawa. It needs to be 10 to the -12. And the lepton number, again, the Majorana mass is lepton number violating. That also needs to be very small. Of course, you can play the same game of making some of these less small, the other ones maybe a bit larger, and come up with a good set of parameters. But you will still require a hierarchy between the lepton number violating terms and lepton number conserving terms. So, and this model, this is not necessarily a model. It's like a scheme, and it doesn't tell you where does this hierarchy come from. And but within all these models is basically what you require to explain neutrino masses is standard model singlet fermions as right-handed neutrinos, and either a very high mass scale or very small lepton number violating parameters. And these are usually bad for collider physics because a standard model singlet fermion means that it doesn't really couple to anything other than just mixing with the neutrinos. If you have a very high mass scale like the seesaw scale, it will be hard to produce at colliders, if not impossible. And small coupling constants, small parameters usually mean that there will be small cross sections at particle colliders. So this is basically the lay of the field, and today I will talk about a specific model that I like working on. It's a supersymmetric model, and then I will tell you how an inverse seesaw mechanism can be very easily, not maybe very easily, but very dynamically can be realized within this model, which this was a model I introduced with Pilar when we were both at Pharmalab. So this is the model we will work with is a U1 R-symmetric SUSY model. And even though supersymmetry might not be too attractive nowadays, it's still nice to play with it as a beyond the standard model physics case. So what is U1 R-symmetric SUSY? And before I go to the neutrino masses, I want to give a summary of U1 R-symmetric SUSY, or MRSSM, it's sometimes called, just to make you a bit more familiar with it. So this is basically just taking the normal MSSM, so minimal supersymmetric model, and then imposing a U1R global U1R symmetry on it. So here R is not necessarily for R parity, it's some new charge, and this U1 is a global symmetry. And I will show you a few superfields. I'm only showing you the ones that will be important for neutrino masses, but the same charge requirements apply to the rest of the superfields as well, like quarks and gluinos and what have you. So here, so with this charge assignments, you only impose the U1R on the supersymmetric sector. So the standard model particles are not charged under this U1R. So the fermions have +1 charge, but fermions have 0 R charge. Similarly, bino has +1 R charge, but the U1 gauge field, standard model U1 gauge field does not. So one thing that happens when you do this is that since bino has now a charge, you cannot write down a Majorana mass for it. You need to introduce new fields to give gauginos mass. So for bino, you need to introduce a singlet field called the Singlino with the opposite R charge. So bino has +1 R charge. This field Singlino has -1 R charge. And you need to do this for other gauginos as well. For the weakinos, you will introduce triplets, and for the gluino, you will introduce an octet. So this is the field content that that is relevant for us basically. But you can even now probably you can see where I will go with this. U1 R-symmetric SUSY has naturally 2 standard model singlet fermions, the bino and the Singlino. Excuse me. To bring the lepton number into the play, instead of U1R, we actually look at a different global symmetry, which is U1R minus L. We can call this R prime, and the same things apply. And in the rest of the talk, I will probably just say U1R, but from now on, I always mean U1R minus L symmetry. Excuse me. So this is the model content, and with this, so a few things happen. As I said, Majorana gaugino masses are not allowed due to the R charges, but we can write down Dirac masses using the bino and the Singlino fields. These are called like soft masses basically. Here D is the a D term, Casparian D term, SUSY from SUSY breaking, and lambda M is the messenger scale. So SUSY is broken in some hidden sector and then is mediated to the visible sector at some scale lambda M, and this gives you a Dirac bino mass. And excuse me, the bino field, like the Dirac bino field, is actually, of course, this Dirac field with B, both the B and S. But when I say, so in the rest of the talk, again, when I say bino, I'm either referring to this field psi or the component bino, and I'm hoping it will be obvious from the slides. So this is the Dirac mass term, and so due to the U1 R-symmetry, the Majorana masses for gauge is not allowed. There are also many other unallowed things, and this actually makes U1 R-symmetric SUSY made U1 R-symmetric SUSY an attractive BSM model because it solves like a few problems with the standard with the MSSM. For example, one of them was the SUSY CP problem. So in MSSM, electron EDM or EDM for other elementary particles are allowed at one loop, but electron EDM puts a very strong constraints on the Lagrangian parameters and SUSY. So it's the same question of if some order one parameter in the Lagrangian needs to be very small, there needs to be an explanation for that smallness. So U1 R-symmetric SUSY actually was introduced to solve that problem. It also solves some other problems like the SUSY flavor problem. It requires less tuning for the Higgs web for heavier stops. So like you can have a few TeV stops and get the same amount of tuning from what you would have gotten if the stops were couple of hundred GeV. So this is the U1 R-symmetric SUSY is fun to play with. So even though the gauginos are I introduced them as Dirac particles, U1R is a global symmetry and it must be broken. And when U1R symmetry is broken, there will actually be Majorana masses that are generated for the gauginos. The Majorana masses can be generated in different ways, but for one of those ways is called anomaly mediation. And in this case, the Majorana mass is proportional to the gravitino mass, and gravitino mass is the reason why a global symmetry is broken anyway. So this will be the case that any U1R symmetry breaking term will be proportional to the gravitino mass. And here M3 is the gravitino mass. The small b tilde is the bino, the Majorana bino mass, and beta is the beta function of the U1 hypercharge. And this is the same thing happens for other gauginos as well. For the Glino, you just have GS here, and for the weakinos, you have the weak coupling constant. So this is a generic property of these models, and you can also have Majorana Singlino masses. Of course, when U1 R symmetry is broken, you are allowed to write these terms. But since again, there is a symmetry reason for those Majorana masses to be there, you can also expect them to be smaller than, for example, the Dirac mass for the bino. So in this case, the bino field, the larger bino field is actually a pseudo-Dirac particle because it has both Dirac and Majorana masses. So even though I kept saying that there are no Majorana masses, there's actually some small Majorana masses, which makes the bino which makes the gauginos in U1 R-symmetric SUSY models pseudo-Dirac particles. So Pilar and I 4 years ago now, time passes, used this fact to make this bino field play a role in generating neutrino masses. And in order to do that, you need to consider effective operators. So, for example, this dimension 6 operators between the spurious, between the D term, the the Higgs and the lepton superfield. So it's a dimension 6 term. So there's a 1 over lambda m squared. Again, lambda m is the messenger scale. This term is U1R minus L conserving. And if you look at the components that are coming from this term, you can write down a neutrino mass operator, which is proportional to, again, this parameter f times the Dirac bino mass over the messenger scale lambda m. So, but this is, this is again U1R minus R conserving. It is lepton number conserving, and it is it acts like a right-handed neutrino. And if you remember the inverse seesaw mechanism case, this is, here bino is what I called n there. And you can do a similar thing for the Singlino, the other component, with the minus R charge and the bino in the bino field. So this is the dimension 5 operator that's only down by 1 power of lambda m. And again, if you look at the components of this supersymmetric operator, you can write down the relevant neutrino mass, which is proportional to the gravitational mass over the messenger scale lambda m. And this is a U1R minus L violating mass term. So, and again, since U1R minus L symmetry is broken by the gravitational mass, this term is also proportional to the gravitational mass. So here the Singlino field is acting like the n prime in the inverse seesaw mechanism. And again, you can write down the Lagrangian of the Lagrangian that includes the bino and bino masses and the neutrino, which will also bring the neutrino masses. So the U1R minus R conserving terms are the Dirac bino mass, capital M, and then the U1R minus L conserving term between the lepton doublet and the bino, and the U1R minus L violating terms are the Majorana mass terms for the bino, and the term that is proportional to the gravitational mass between the lepton doublet and the Singlino. So this is, again, if you here bino is n and s is n prime, and this is exactly like an inverse seesaw scenario. And in this case, this the pseudo-Dirac field psi is the right-handed neutrino field, basically pseudo-Dirac right-handed neutrino field. And from now on, I will call this field psi a bino, where n is replaced by nu, but it's exactly pronounced like a bino. And so you can take this Lagrangian, and after electroweak symmetry breaking, it gives you a mass matrix for the neutrino fields. Here, the 3×3 zero part is the standard model neutrinos, and the rest comes from the bino and the Singlino interactions. Excuse me. And for all of this talk, I am assuming that there's no mixing between the bino and Higgsino and Weakinos, which you can do in for certain parameters in the larger MRSSM U1 R-symmetric SUSY, basically. But that is not hard to achieve. So let's assume that there is one neutrino as a pure bino. And the parameters, the vector fields YNG are given, basically you calculate them from the PMNS matrix to get the correct neutrino masses. So this is a neutrino mass matrix. You can find the eigenvalues of this matrix, which gives you the light neutrino masses. And these are the eigenvalues for a normal hierarchy. And assuming the Dirac bino mass is larger than the electroweak scale, the Higgs wave V, since there's only 2 new degrees of freedom in the neutrino sector, there are only 2 masses. So we expect for normal hierarchy, we expect M1 to be 0, and M2 and M3 are given here. So rho is 0.7. It just comes from the neutrino mass splittings, and again, the neutrino masses are proportional to the gravitational mass, and inversely proportional to the messenger scale. So the messenger scale is kind of playing the role of the Dirac mass in the inverse seesaw mechanism, and the gravitational mass is playing the role of the Majorana mass. And this is where the hierarchy between neutrino masses and the other fermions are coming. So we can look at the parameter space, for the gravitino mass and lambda m. That gives us the correct neutrino mass scale. So here in this plot, the x-axis is lambda m, y-axis is the gravitino mass, and on these lines, you get the correct neutrino mass scales, and the solid line is for normal hierarchy, normal ordering, and the dashed line is inverted hierarchy. Excuse me. So you can see, for example, for like a 100 TeV messenger scale, you need a few keV gravitino to get the correct neutrino masses. All right. So this is this can be considered as the parameter region that nicely gives the correct neutrino masses for U1R MSSM. So this is what we require. How about constraints? So first of all, there's constraints from low energy experiments or low energy phenomena like mu to E gamma decays or tau to E gamma, tau to mu gamma decays. These are lepton flavor violating decays of the charged leptons. Of course, when you add new leptons into the mix of neutrinos, we expect lepton flavor violation, and we've been looking for these branching fractions, and the most constraining of these branching fractions is coming from MEG for mu to E gamma, and that puts a constraint on actually just lambda m at 30 TeV. So it is not currently, it's not touching the parameter regime that we are interested in. There will be better constraints coming from lepton conversion near nuclei, for example, mu to E conversion near aluminum. This will be searched for at the mu to E experiment at Fermilab. It was supposed to start running about this summer. I'm not sure what it's doing right now. But the projected reach of mu to E gamma will go up to 80 TeV, 70 TeV, and it might even go up to 140 TeV for the messenger scale. Again, these are not actually probing, in this scenario, these are not probing the gravitino mass, but only the messenger scale, and from that messenger scale, we know what gravitino mass we will require. So this is basically, so these are the constraints or the projected constraints from low energy experiments. There could be constraints from Jones double base decay as well, but actually they are not as good as the mu to E gamma constraints. So we looked at them, but they weren't as constraining. So this is the parameter regime that we focused on, and so this is what Pilar and I did. And later with some other collaborators, we looked at constraints from the LHC. So again, the low energy experiments are can be used to probe the messenger scale, and that gives us what we need for the gravitino mass. But this is not saying anything about the bino mass. The bino mass can be probed at the LHC, or can be searched for at the LHC. Before going to this LHC constraints on this model, I want to emphasize one thing about right-hand neutrinos and the LHC. Right-hand neutrinos, again, these are singlets, and they're only produced via mixing with the standard model neutrinos in electroweak processes. So you are looking for producing a neutrino basically, and then it mixes with the right-hand neutrino. So so you always pay the mixing angle price, which is already about 10 to the minus 5 or so, on top of an electroweak cross section. So these tend to get very small very quickly. So that's it is. Quite a bit hard to search for right-hand neutrinos that are tied to the neutrino masses at the LHC. But for a supersymmetric bino, this is not really the case, because bino can be produced in many, even in QCD processes at the LHC. before going to the LHC phenomenology, I want to give you the particle spectrum that we assume, because as MSSM has lots of particles, and we introduce another symmetry on top of it, which made us, which required us to include even more particles. So there are a lot of particles and scales in the question, but they are, they kind of are categorized into some hierarchies actually. So the lightest supersymmetric particle here is the gravitino, and its mass will be about 10 keV. And then you have the electroweak scale, of course, 100 GeV. The SUSY particles, supersymmetric particles, are heavier than this. Again, we assume that the lightest neutrino is a pure bino, and quarks and leptons are heavier than the bino. So next to lightest particle is the pure bino, and all the other particles, like the other neutrinos, chadrinos, and gluinos, are a bit heavier, and we assume that they are decoupled. So this is the particle spectrum. Particle spectrum we assume. So with that, we can look at how bino will be produced. So with the spectrum, the bino production mostly happens via gluon fusion, and then producing a squark anti-squark pair, and then the squark decays into a quark and a bino. And everything here is produced in pairs, fermion pairs, because of the U1 R-symmetry. And you compare that the cross section, this bino anti-bino, comparing this even the squark pair production cross section to, for example, MSSM, you can see that the cross sections here are a bit smaller. This is again because of the U1 R symmetry. Some channels are not available, so the cross section is smaller. And the cross section is smaller, LHC constraints tend to get a bit looser. So this is one thing that is good and bad about the U1 R symmetric SUSY models. So this is the production channel we focus on for the bino. And of course, after being produced, bino can decay in a few different ways. And I will divide these, divide the bino, the phenomenology into two sections. One of them is bino decays if the bino is heavier than basically the Z boson. So that's assuming bino is heavier than 80 to 100 GeV or so. And the second part I will talk about is if the bino is lighter. So, okay, so this a bino as heavy as this can decay in a few different ways. So first of all, it doesn't need to be this heavy, but it can always decay to a gravitino and a photon. This is a very small width because it is expressed by the Planck mass. And for again heavier binos, through its mixing with the neutrino, it can decay to W and a charged lepton, a Z and a neutrino, and a Higgs and a neutrino. The total width for this process goes like the bino mass cube over lambda m square. And for a bino mass of 500 GeV and a lambda m of 100 TeV, this is about 10 MeV or so. So it is it's quite large. So the bino decays promptly. And when it decays to a lot of things. It decays to jets, leptons, and missing energy in the form of neutrinos. So, for example, this is some of the decay channels. And this is the largest fraction, branching fraction of the decay channels, which is to jets plus jets plus missing energy. So this is the, excuse me, again, production via the gluon fusion, and then decays to jets plus missing energy is about 25% of the bino decays. And it also gives us the most constraining search. We can use a jets plus mass search by Atlas, which was done for 36 inverse femtobarn with 36 inverse femtobarn data. So we basically recast that search for this model, and to give a bit of more idea about what the search is doing is that it has 24 signal regions. The signal regions are divided into how many jets are in the final stage. They look at between 2 and 6 jets, and each region, many of these regions with a specific jet number is then divided into other regions depending on what this parameter called MF is. MF is a scalar sum of the leading jets, and the missing energy in all the signal regions is larger than 250 GeV, and some of the signal regions require even more missing energy, and in all of the signal regions, the PT of the leading jet is, the PT cut is 50 GeV, and again, the specific signal regions require sometimes different cuts as well. Excuse me. So this is the the search, and then we recast that search for our model. We produce the events with MET graph. The region of interest is, again, we look at the bino mass that is a bit heavier than the gauge boson masses, so that it can just decay into a gauge boson and leptons, or Higgs and a neutrino. We also don't look at the case. We also require that the bino is lighter than the squark by at least 25 GeV. So these the stripped grayish regions are regions that we haven't looked at. So they're out of the region of interest, and this plot is, the x-axis is the squark mass and the y-axis is the bino mass. The shaded regions, the darker red shaded region is the exclusion region by the 36 inverse femtobarn atlas jets+MET search. The lighter reddish shaded region is what we expect to exclude with 300 inverse femtobarn data. So this is a forecast. The lighter region is the forecast. So from this, you can see that for example, for a bino mass of 500 GeV, the squark masses only up to 900 GeV or so are excluded. You can have, for example, a 1 TeV squark within the scenario, which is much looser than the constraints on normal SUSY. This is because of both the particle spectrum and also what the bino is decaying into. And with further data, of course, this exclusion region will, well, I don't want to say just the exclusion region will get larger. Maybe they will find something. So anyway, so this is what we did with Paddy and Julia, and follow up to our model with Pilar, my model with Pilar. So this is the jets+MET searches, which can be used as exclusion. There's actually another final state which is very interesting. This is a final state with leptons in it, charged leptons in it. So this is, it will again have jets, but also a charged lepton. This is about 15% branching fraction. Excuse me. And this final state can be searched for with leptoquark searches. So you can kind of combine the largest PT lepton with one or two of the jets, which kind of acts like a leptoquark in that sense. And then you can use leptoquark searches to you can recast leptoquark searches to search for this final state as well, which we looked at for with CMS leptoquark searches, especially second generation leptoquark searches. Now, this search is not as constraining as the jets+MET search. Signal to background is too small. So here, what you're looking at is like number of events that are produced at the LHC at 13 TeV, and the x-axis is again the leptoquark mass for leptoquark searches, but in this case, it is not quite the bino mass. It is just a combination of the leading PT charged lepton and the leading PT jet. Excuse me. And the green and blue blue lines are what you expect from a bino with 500 GeV and 700 GeV respectively, with a squark mass of 900 GeV. So since the error bars are too large, this is this search is not constraining, and this plot, even though a very nice plot, it didn't make it to our paper because it wasn't as constraining. But I wanted to mention this specific final state because it's actually a smoking gun signal for this model. So if we look at lepton final states, and these are coming from, again, bino neutrino mixing and then decays into leptons and W's. The mixing angles, the lepton couplings are fully determined by the neutrino mixing matrix. So here, what is important is this y vector, and this is again fully determined from the neutrino mixing parameters. And if we look at that and calculate the relative rates of, for example, electron final states and muon final states, this is again just determined by the neutrino mixing parameters. For example, an EE to mu relative rate will be 1 to 16. Or you can look at lepton and neutrino final states, and in this case, an E nu to mu nu final relative rates will be 1 to 2. So this is just determined in this model, and it will be a very nice signal if you can measure, if you can see it in both an electron and a muon channel, and then you can compare the rates. That will tell you if the bino or if the particle involved in that decay is playing any role in neutrino mass generation. So that's why I wanted to point this signal out. Okay, so this is the so this was for heavier bino, what we can expect from the LHC. And currently I'm working on, again with Pilar and Julia, on looking at a lighter bino, which can be long-lived. So this is the bino, if the bino is lighter than the gauge bosons. And I think I forgot to mention, but for the first LHC part, we assumed we set lambda m at 100 TeV, and we will continue to do so for this case as well. So if the bino is light, it can't decay to on-shell W's. It will decay to jets plus other things through off-shell gauge bosons and Higgses. So, and the final state will be instead of the 2-body, there's a 3-body final state, and you're integrating out a W. So the decay width for in this case will be much smaller. It goes like GF squared, so 1 over MW to the 4, and over 1 over 4 pi cube is just the phase space, coming from a phase space integral, basically. So the decay width in this case is much smaller than the decay width what decay width you expect from a heavier bino. So this will actually give you a longer lived bino at the LHC for, of course, certain bino masses. So again, setting lambda m at 100 TeV, you can just look at the decay length of the bino for different bino masses, and this is what I'm kind of showing on the plot here. So this is not so the x-axis is the bino mass, and y-axis here is a probability of decaying inside one of these detectors. So these are many different detectors at the LHC. Some of them are inside the tunnel, some of them are on top of the tunnel. So this is a very rudimentary plot. Please don't take this to be very seriously. But if the bino is, for example, if the bino has mass 50 GeV, okay, so you look at the decay width, and even though it lives maybe long enough, it still decays inside the Atlas detector. If the bino is a bit lighter, its decay width becomes smaller and smaller, hence the decay length is becoming larger and larger. So it could escape the Atlas detector. It could go into one of these other experiments, for example, phaser or Methuselah. So phaser is a bit further, it's smaller, so there's less chance of decaying inside it. Methuselah is, again, is also as further, but it's a bit larger, so there's a larger chance of decaying inside Methuselah. And Codex B similarly is closer actually, and also larger than phaser, so there's a better chance of decaying in Codex B. And I will tell you what these experiments are in very shortly as well. So this is this is just basically to make the point that for these bino masses, especially for masses lighter than 20 GeV or so, it will be long-lived enough to to be able to search for some of these experiments, which is quite fun, including Atlas, especially with Atlas long-lived particle searches as well. Excuse me. So another way to look at this is, we just kind of first tell what all these experiments are. If you haven't heard about some of them. So phaser is actually built, I assume. So when the LHC starts running again, phaser also will be running. So phaser is a detector. It's about 1 meter high or wide and 10 meters long. It's inside the LHC tunnel in front of Atlas. It is it's in the forward direction. So it is in one of the side tunnels, in front of Atlas, and it gets whatever is escaping the Atlas detector in the forward region. Methuselah is I don't know the current status of Methuselah, but it is it's a detector actually on top of, it's on Earth, so it's outside. It's not inside the tunnel, and on top of Atlas, a bit to the side maybe. It's about 100 meters away from Atlas, and then it's 20 by 20 meters, so it's quite large detector. Codex B is Codex B is on top of LHC B. So it is, getting getting the particles that are produced at LHC B interaction point. So these are the 3 detectors we are looking at right now. Atlas itself is, large, is 25 meters diameter. How can I say this? So the Atlas also can look for long-lived particles that are decaying inside Atlas, but living longer than a millimeter or so. So in this, is there a question? All right. So what I'm trying to show in this plot is a few things. So first of all, this is on the x-axis we have squark masses, and on the y-axis we have the bino mass. Of course, the squark mass tells you the cross section, the bino production cross section at the LHC. So for heavier squarks, there are less squark pairs produced, and that means there are less bino pairs produced. So lighter squarks are of course better. Excuse me. So the squark mass is controlling the cross section, and the bino mass is controlling the decay length in the scenario. And all these shaded regions means that at least one bino decays inside a detector within the shaded region. So the boundary is basically one event. And as you have smaller and smaller squark masses, you will have more and more events in that specific detector. It doesn't mean that you will be able to measure that event though. For example, for a very light bino, like a 1 GeV bino, even though it can decay at Atlas, doesn't mean that Atlas will be able to measure a 1 GeV event. So this is, this is just to, so any constraints from these experiments will be necessarily smaller than what the region that I'm showing you. But okay, so the orange region, the orangish region here is the Atlas detector basically. So inside this region, these particles decay, decay inside Atlas, or there's at least one particle decaying in Atlas, and this is with 3 inverse attobarn of data. The phaser region is the smallest. As I said, phaser is in the very forward region, so there's less there are less stuff going in the forward direction than not, and phaser is kind of small. It's 1 meter, so it's the smallest region is phaser. Methuselah is a bit larger, and again, Codex B is a bit larger as well. But it's very nice that all of these regions are actually complementary in a way. And for, of course, heavier, for bino masses that are, 50 GB or heavier, bino actually decays promptly. So that is, again, the same search as, I talked about, because it's the prompt decays. And for, very lighter binos and also very heavier quark masses, we won't be able to see any decay events of the bino. So it will be just, it will be seen as a missing energy, the bino missing energy. So this is, again, very ongoing work. This is a preliminary plot. It is just guesstimates of the regions. And at the end, what we want to do is basically have a fuller idea of the bino quark mass region. So my earlier work with Julia and Paddy is here the red solid region. So this is the exclusion from jets+MET search, Atlas searches with 36 immersed centibarn of data. And as we go into smaller bino masses, our ongoing work will basically tell how we can use these experiments to probe and or exclude more of the lighter bino masses. And this jets+MET search, of course, still can be used for these other regions as well, because if bino is long-lived enough to, longer lived than a millimeter or so, the jets+MET searches will just see that as jets plus missing energy as the bino. So this red solid region will go down a bit as well, or will probe the regions that are lighter than 100 GB bino as well, which is also again ongoing work. So it will be nice to scan all of this mass region. And excuse me. So this is the ongoing work, and even further down the road, it will be nice to look at leptoquark searches again to see if we can exploit those to see the smoking gun signals of such a model. There's also, I only use bino for the neutrino mass generation, but this U1 R-symmetric SUSY also has vinos, which are electroweak triplets, which can also be used maybe in a type 3 seesaw kind of scenario. So that will be interesting as well. So one thing that, again, this model predicts is that there will be a massless neutrino mass eigenstates, and if we measure that all three eigenstates are massive, then that would require us to go beyond this model as well. There's also, one thing one of the parameters here is the gravitino mass, which is again order 10 kV or so. This actually, again, with some back of the envelope calculations, we think the gravitino could be a dark matter candidate, and it will be nice to flesh that out further as well. So also with the longer lived bino part, there could be a metal-antimatter symmetry generation scenario through either baryogenesis or leptogenesis. And this, I haven't thought about it much yet, but something that I'm very interested in. Metal-antimatter symmetry is something that I am very interested in, and I would like to think about model building in that direction as well. So this is it.
Okay, thanks really a lot. Hope that you see people clapping virtually, obviously. So let's see if there is any question to this nice talk. Thanks again for the talk. You can just unmute yourself and make the question or the comment. In the meantime, I saw some exchange of email of the crisis that Belen was mentioning before the beginning of the talk, and I see someone already left for that reason. So
oh, I see.
If there is no questions, let me ask you something. So the observable that you're considering are pretty generic, no? So is there a very smoking gun that you can think about? Or it could be that another model, for example, with extra fermions, vector-like fermions, for example, so not really leptoquarks that you spoke about, and not maybe in supersymmetric context, but just in I don't know, a gauge flavor model, where indeed usually you do introduce vector-like quarks and vector-like leptons, may simulate somehow the same signals, or is there a smoking gun what you're speaking about?
Is this a good question? I don't know off the top of my head. I should think about this. The one thing I will say for this one, so the smoking gun is the, you know, the rates, the relative rates of the final state. But the other part of this is that we have large cross sections because these are produced via gluon fission, for example. So, you know, that part is also like kind of immovable in a way. So you can, I don't know if you can think of a scenario where you combine those two, like, you know, the particle was produced not from an electroweak initial state, but a QCD initial state, and then it decayed via neutrino mixing. So maybe like combining that would be, you know, a smoking gun for this specific model, basically.
I see, I see. But it's good that there is one specific smoking gun.
Yeah.
It's very difficult to find one, actually.
Yeah, again, it's not, yeah, it is very nice that it's there. I hope it will be measured.
Okay. Is there any question, a comment? Okay, doesn't seem so. So thanks again, really a lot. And hope you have a nice day, because you have 20 hours now in front of you. So thanks a lot, Seyda. I hope to see you next year here in Madrid. Personally.
I hope so too. Thank you very much. Have a good evening.
Thanks a lot. Bye. Thank you.
Bye.